Now we have the chain rule, the product rule, the quotient rule, each of which build on our basic differentiation properties to allow us to tackle a wide variety of differentiation cases. Sometimes, though, we have to use those rules in conjunction with one another, and we'll see that happen in a few different examples with 8 through 10. In example 8, we're taking the derivative of the natural log of negative x to the fourth plus e to the 2x. This is a composite function, so we'll apply the chain rule to get 1 over negative x to the fourth plus e to the 2x times the derivative of that interior function and the derivative of that interior function will be negative 4x cubed plus the derivative of e to the 2x, which is itself a composite function. So this will become e to the 2x times the derivative of 2x. Meaning we have 1 over negative x to the fourth plus e to the 2x times negative 4x cubed. And then once we take the derivative of 2x, that will be 2. So we'll get plus 2e to the 2x. From there, we could just condense this down and write that second factor as the numerator of our expression to get negative 4x cubed plus 2e to the 2x all over negative x to the fourth plus e to the 2x. In example 9, we have a composite function again. So to find d over dx of r of x, we'll get e to the negative x to the fourth plus the natural log of 5x times the derivative of that interior function When we take the derivative of that interior function, we get negative 4x cubed plus the derivative, oh, I should put that prime there if I didn't include that above. To take the derivative of the natural log of 5x, we have a composite function. So this will be 1 over 5x times the derivative of 5x. So we'll get e to the negative x to the fourth plus the natural log of 5x times negative 4x cubed plus the derivative of 5x will be 5, and the 5's will cancel, so we'll be left with just 1 over x. In examples 8 and 9, we had to use 2 iterations of the chain rule. Now what we'll see is the chain rule used in conjunction with the quotient rule, since we have a function in the numerator and a function in the denominator. To find dc over dx, we'll take the derivative of the numerator, so that will give us 4 times x minus 3 cubed minus 4x times the derivative of this composite function, so that will be 3 times this interior function, x minus 3, raised to the second power, times the derivative of that interior function, all over x minus 3 to the third power squared. When we take the derivative of that interior function we had in the numerator, that will just be 1. And still all over that denominator squared. So this will be x minus 3 raised to the third power raised to the second power. So that'll be raised to the sixth power once we multiply those together. Simplifying a little bit here gives us 4 times x minus 3 to the third power minus 12x x minus 3 squared all over x minus 3 to the sixth. And now we want to look for anything that's common between those two terms in the numerator that we can factor out. In this case, it'll be 4 times x minus 3 squared, which will leave us with x minus 3 in the first term minus 3x in the second term, all over x minus 3 to the sixth power in the denominator. X minus 3 squared will cancel with 2 of the x minus 3's in the denominator. Leaving us with 4. And then inside those parentheses, we'll end up with x minus 3 minus 3x. Combining like terms will give us minus 2x minus 3 all over x minus 3 to the fourth. And then the very last step that we can take here, just to factor out one more common factor, is between negative 2x and minus 3. We can factor out a negative 1 to rewrite this as negative 4 times 2x plus 3 all over the quantity x minus 3 to the fourth power.